Hi, I'm Victor. I'm going to talk about a bit of my PhD research, what I'm trying to accomplish, what I already accomplished, and some of my results, and what I'm doing right now. And so, as a general overview, I'm from Brazil, and my supervisor is Fabio Cosman there. And for the 6 months I'm here, Serena is my supervisor. And I'm working on assessing the quality of arguments using a neuro-symbolic approach. And this picture here outlines the system I'm trying to create. I'll go into more detail later. So, what was the motivation, the initial motivation for my PhD? It was that nowadays, because of large language models, it's easier than ever to create texts that justify false claims. And here I have a simple example that we were able to make ChatGPT justify that. Say that Miles Davis, the jazz musician, was a major influence on both Amadeus Mozart, which is obviously false because of their lifetimes. But we can make ChatGPT justify that. So one of the ideas is how can we identify false claims? And the strategy, the hypothesis is that by analyzing the quality of the argumentative structure of such texts, we might be able to identify them. And the intuition is that if, so for instance, the text trying to justify that Miles Davis is an influence to Mozart, eventually it will run into a contradiction or will resort to false other problematic argumentations to do so. So the first step I took in my research was to try to empirically evaluate how large language models argue, in particular ChatGPT, which led to this publication. And to do that, what we did as a group, was to create a methodology that created artificial texts based on contradictory themes, such as the one I told you from Miles Davis and Mozart. And we have had some annotators who annotated this text for argument mining, automatic essay scoring, and based on the automatic essay scoring tasks, they created a framework to analyze the argument quality of each text. So when I talk about argument mining, just to make sure everyone understands what I'm talking about these three different tasks, and that's span identification, component classification, relation classification. So quickly, to explain it quickly, if we have a text first and we need to extract its argumentative structure, the first thing we do is to find out where are the argumentative parts. That's the first task, span identification. Here in the picture, we can see suppose this is part of a larger text, and we found those two components. After that, we need to identify which kind of component according to our framework it is. So now, in this instance, both are premises. And lastly, we have to identify which components are related and how. And so in our example here, the second premise supports the first one. So that's what I mean by argument mining. And okay, so the methodology to create those texts, so ChatGPT text was to create an academic scenario that was designed to induce errors, because we wanted to have examples of both instances where ChatGPT was able to produce good arguments and also instances where it was not, and to see which was prevalent. And so the methodology was simple. First, we came up with some themes that contained some absurdities, such as Miles Davis being an inspiration for Mozart. Then we have the first prompt. The first prompt asks ChatGPT to produce a student essay, argumentative essay, justifying that claim. And but sometimes ChatGPT realizes it's talking nonsense. So we wanted to be sure that at least for one theme, at least one of the texts would be bad. So we had a second prompt that asks ChatGPT to pretend it's a professor correcting the first text into the same format, so I mean argumentative essay. And this way we ensure that we would almost always have examples of both good and bad arguments that would explain or counter-explain the claim we provided. Using that methodology, we produced 172 texts, and we explicitly annotated contradictions and inconsistencies, so we could analyze them. And one thing that was interesting is that generating such texts, after we had this methodology, generating the texts was very quick, which is interesting because for a human, writing such texts would take a lot of time. So based on the annotators had a background in correcting argumentative essays, so they analyzed the argumentation part of the text through that lens, and they used those criteria, no repetition of arguments, no contradictions, and so on. And based on that, they came up with three different kinds of arguments they found in the text. One they considered good, and that's the kind of arguments that's solid, very good argumentation. And when it's defending a true topic, for instance, a true topic would be, okay, Miles Davis is not an inspiration for Mozart, and the text would justify why. The second one would be bad argumentation, and it doesn't matter if that's a true topic or not. The text was not able to provide a compelling argument for that. And the third one is ugly because it's solid argumentation, very, very well argued, but defending a false claim. So it begins with false premises, but it's able to use them to provide a compelling argument to the false claim. And one interesting thing here is that almost half of the texts were bad, which suggests that analyzing the argumentative structure is one way to help identify such texts. And a second interesting thing we find out, and for this we did the following experiment. We trained our model on our data and then tested it on human-generated data of the same kind. By same kind, I mean both are argumentative texts, argumentative essays. And we did the reverse test, trained it on the human-generated data and tested it on our data, our artificial data. And the interesting was that using artificial data did help a lot in argument mining tests for the human-generated data and vice versa, which suggests that even though ChatGPT most of the time is not able to provide compelling arguments, it does use argumentative structures that we as humans do. So that was interesting. And so the main conclusions of the first step of my research was that yes, artificial data does relate well with human argumentation in terms of argument mining. And evaluating argumentative structure does seem to be a good way to detect those false arguments. And we also had this created this methodology and annotated one more data set for argument mining and automatic essay scoring. So now that we have this intuition and it seems to be true that analyzing the structure of the argumentative text does help to identify them, I need to make clear what I mean by analyze this structure. So I will go through what I mean by argument reasoning. How do I reason using an argumentative structure? And the idea here in the picture, I show you what my system is, what the system I'm trying to construct is supposed to do. It receives a text, extracts its argumentative structure, that's the argument mining module. Then the argument reasoning module reasons about that structure, and the argument quality module will receive all of that input and output a probability that this text contains a good or bad argument. So what I mean by argumentation reasoning, I based my research on Dung's paper. That's one very famous paper for abstract argumentation. And basically what abstract argumentation does, it abstracts away the content of each argument, each node, and we want to identify which arguments are acceptable or not given the graph structure. And it doesn't matter what the content of the arguments are, only their relations to each other. And originally, the paper only talks about the tag relations, but there are variants with support relations as well. So just to give you an intuition, the idea is to have semantics. Each semantics can be understood as a rational way in which we define which arguments are acceptable or not, given the graph structure. And given these semantics, we can find the acceptable arguments and so on. And if you are familiar with logic programming, you already saw that before because that's very similar. And indeed, since the beginning of abstract argumentation, we know about this connection between abstract argumentation and logic programming. And some recent results showed that to most semantics from both logic programming and abstract argumentation, the results are the same, so the semantics are equivalent. But there are limitations to those equivalences, and that's what I mean by equivalence. Those results, if I use the formalism and translate it to the other, and I use the semantics, they wield the same results. And this does happen to several semantics, but it doesn't for this pair, L stable and semi stable, even though they do share the definition on each formalism. So just as an example here, I have a logic program on left and abstract argumentation framework on right. And the abstract argumentation framework is a translation from the logic program. And I apply the L-stable semantics to the logic program and the semi-stable semantics to the argumentation, abstract argumentation framework. And as we can see, the first is true, false, and undecided, the first, second, and third. And as we can see, the first result here, for logic programming, we get 2 undecided atoms, and for argumentation, we get 3. And something similar happens to the same result, so they're not equivalent. So the first thing we did to address that was to change a bit how we define the argumentation framework. So instead of abstracting all the content away, we keep the argument conclusion. So in doing so, we change how we evaluate the semantics. So instead of evaluating at the argument level, we evaluate it at the conclusion level. And by doing that, we achieve an equivalence between both formalisms, both logic programming and argumentation frameworks. And but it's still not enough to achieve a 1-1 equivalence, because traditionally these algorithms did not use the positive atoms from the logic programming. So if we translated logic programming to abstract argumentation back to logic programming, we lost some information. So to solve that, we simply added the support relation to the graph, argumentation graph. And in doing so, we achieved a 1-to-1 equivalence between both those formalisms. And why is that so important? Because in doing so, we can translate our argumentation graph or argumentation structure to logic programming and use its tools to achieve the results we want. So we can use tools that are already available for logic programming to do our argument reasoning. And one thing you might be wondering is why we went to such extreme efforts just to have equivalence between that specific semantics. So I will explain why. In logic programming, usually people rely either on the well-founded or stable semantics. And the well-founded is equivalent to the grounded semantics in argumentation. And the idea is very simple. We believe that the L-stable semantics, or the same stable one for argumentation, is the most appropriate for argument reasoning. And the reason is very simple. Suppose we have this argumentation graph here We have J, H, and J in G, and the edges symbolize attack relations. So J and G attack each other, so they're contradictory, and both attack H. If we use the well-founded or grounded semantics to reason on this graph, we will get the result that all arguments are undefined. And that is because this semantics is supposed to be very skeptical. So it will only accept arguments that we have no way of not accepting. So the set of acceptable arguments will be minimal. So the problem is, if we look in this graph, it doesn't matter if we favor J or G, H will not be acceptable. And that's something important for the argumentation part. We can say by analyze this that, okay, H should not be acceptable. And that's the problem with the well-founded grounded semantics, and that's why we don't use it. But the stable semantics does allow for that conclusion that I said. So it doesn't matter if we choose to accept J or G, H is discarded. But the stable semantic has another problem. So suppose we have a second graph, and that's basically the same as the first, but with the fourth argument I, and it's self-contradictory. The stable semantics does not allow for undefined atoms or arguments, and which means that it is not able to reason when such an atom that contradicts itself arises. And we don't, once again, we want to be sure that H is rejected. Because of this structure, we can see that it doesn't matter which argument we accept, H should be discarded. So instead of using the stable semantics, we use the same stable one or the L stable one, and which allows us to conclude that H should be discarded, and it allows Y that's self-contradictory to be undefined. So the definition of the same stable semantics is basically the same stable semantics, but we allow for the minimal set of undefined atoms and not no undefined atoms. To illustrate why it's important, I compare the system we designed to do the argument reasoning with another one from the literature. I forgot to provide the reference. I will do that. That's this SM per blog. And what they do is also to explore the equivalence between logic programming and argumentation, but they use the stable semantics. So here on the left, we have, for the same logic program, we have their results and ours. And I will not go into too much detail on how we came up with those probabilities. But if you want, we can talk about it later. But the main thing to see here is that by using the stable semantics, they make most of the probability max fall into the inconsistent label. Which is undesirable for argumentation, while for our case, only the label only a small part of the probability mass is left there in the undefined space. So that's one advantage of using the L-Cradle semantics, and that explains why we went to such lengths to make them equivalent in argumentation and logic programming. So now we can assess which arguments are acceptable or not, but we need to define how it helps us to assess the quality argument, the argument quality, the argumentative structure quality. So the idea is good argumentative text should at least be able to provide a compelling argument or to justify its main points, so its major claims. It might have some internal problems, but it's able to justify its major claims. So that's the basic idea. So what I do is to have a second logic program, and I think the next here I will be able to explain it a little better, and that's what I've been doing since I arrived, is to construct that system. So I have that second logic program that uses the probability of the component being a major claim or the main point of the text and the probability that is accepted given the argumentative structure, and combines those informations, that information to give me a probability that this argument is sound. In doing so, I have a probability of this probability being good, of this text containing a good argumentative structure. So just to give you a final overview, basically what I do is, what I want to do, I have receive an argumentative text, I extract this structure, so span detection task, it extracts its components. The component classification gives me a probability of each component being a type of component, so a major claim, or a premise. The relation classification test builds the graph, the argumentation graph. So it gives me not only the graph, but the probability that this graph is the right one. And by having this graph, I can reason with them by using those tools I talked to you about. And by reason, the output of this reasoning is the probability that each argument is acceptable. And given the probability that each atom or argument is acceptable and the probability that each argument is the main point of the text, we can combine this information in what we call argumentation quality program and produce a probability that the text as a whole is good. So far, I've obtained some promising results with some limitations, but the results have been promising so far. And if you are interested, I can talk more about the results I got so far. And that's it for my presentation. I hope you enjoyed it.